We'll start with the electric field generated by the dipole shown, equal magnitude but opposite sign charges. We'll investigate Gauss's law for a few different surfaces. Recall that Gauss's law says that the flux through a closed surface is proportional to the charge enclosed. Let's start with a sphere that encloses both charges as shown. From Gauss's law, we expect that the total flux passing through the surface of the sphere should be zero, the total charge enclosed. As always, we can identify the flux to the surface of this sphere as the total number of lines leaving the surface. On the left-hand side, we see a set of lines leaving the sphere as indicated by the blue arrows. These same field lines curve around and then enter the surface of the sphere on the right side as indicated by the red arrows. The total flux through the surface is therefore zero. For the lines that leave the surface, the product E dot dA is positive, while for the lines that enter the surface, the product E dot dA is negative. When we integrate over the entire surface of the sphere, we will get zero flux, in accordance with Gauss's law. We'll now replace this large sphere with two smaller spheres, each one enclosing just one of the charges as shown. Here, all of the field lines passing through the surface of the sphere on the left are leaving the sphere, the blue arrows. Consequently, the charge enclosed by the sphere on the left must be positive. E dot dA is positive everywhere. Similarly, all of the field lines passing through the surface of the sphere on the right are entering the sphere, the red arrows, indicating the flux is negative. E dot dA is negative everywhere, and therefore the charge inside the sphere must be negative. Since we have identical numbers of lines that leave the sphere on the left as that enter the sphere on the right, we see that the magnitudes of the charges inside each sphere must be equal, in agreement with our initial assumption.